An AI can produce a paragraph in seconds, but it never writes the paragraph all at once. At this instant, the model is allowed to choose only one thing, the next token. Take this prompt. A prism splits white light into... You can probably feel several endings competing. Colors, a rainbow, a spectrum, maybe something less useful. The model faces the same kind of choice, but it does not see words floating in its head. It produces a score for every token in its vocabulary, turns those scores into a distribution, selects one token, attaches it to the prompt, and starts again. That loop is the small machine inside every long answer. The tempting picture is that the model writes a complete sentence somewhere backstage, then reveals it piece by piece. That is not what an autoregressive language model does. There is no finished answer waiting behind the screen. There is only the text available now and a computation that asks what could come next. Start with the token ribbon from the previous episode. Each token enters the transformer with information about its content and position. Inside a decoder-only model, a causal mask controls which positions can use which other positions. The first position can use only itself, the next can use the first two, the third can use the first three. The allowed connections form a triangle. This does not mean the computer must process the existing row one token at a time. The positions can be computed together. The mask simply prevents an earlier position from using a later one. For generation, one position matters most, the last position currently in the prompt. Its contextual vector carries the model's latest internal representation of the prefix. It is not a sentence summary written in English. It is a long list of learned numerical features shaped by all the layers below it. Now the model applies one final learned projection. Imagine the contextual vector shining through a large stencil with one opening for every vocabulary token. Out comes one score per token. These scores are called logits. A logit is not yet a probability. It can be positive or negative, and its absolute value is less important than how it compares with the other logits in the same choice. For our prism prompt, use 4 toy candidates. Suppose spectrum receives a logit of 2.0, colors gets 1.2, rainbow gets 0.3, darkness gets minus 0.4. Real models score thousands of possible tokens. We are showing 4 because the geometry is easier to inspect. These values are invented for the explanation. The logits now pass through a normalization called Softmax. We do not need the full equation here. Geometrically, Softmax turns the uneven skyline of scores into non-negative probability mass that adds up to 1. Higher logits receive more mass, but lower candidates usually do not vanish. Now we have a distribution, not a verdict. The simplest rule is greedy decoding. Choose the token with the highest current probability. In our toy example, that means spectrum. Greedy decoding is deterministic for a fixed model, prompt, and implementation, but deterministic does not mean correct. It merely means we always take the tallest bar. Sampling uses the same distribution differently. Imagine dropping a marker onto the probability arc. Wide regions are more likely to catch it, but a narrow region can still win. Run the same prompt again, and the marker may land somewhere else. That is why 2 generated answers can differ even when both are plausible. But randomness is not the only reason outputs change. The model, prompt, system instructions, numerical implementation, and decoding settings can all change the distribution before a token is selected. Temperature changes the shape of that distribution. Lower temperature makes the high logits dominate more sharply. Higher temperature spreads more mass toward alternatives. At very low temperature, sampling begins to resemble greedy selection. At higher temperature, variety increases, along with the chance of unlikely continuations. Temperature does not measure creativity inside the model, and turning it down does not make the answer true. It only changes how concentrated the next token distribution becomes. 2 other controls place fences around the same ranked distribution. Top K keeps a fixed number of the highest ranked tokens and removes the rest before sampling. If K equals 3, only the top 3 remain, even if the third candidate is much less likely than the first 2. Top P, also called nucleus sampling, uses a probability threshold instead of a fixed count. Starting from the most likely token, it keeps adding candidates until their cumulative probability reaches P. A confident distribution may need only 2 tokens. A flatter distribution may need 10. The fence changes size with the distribution. Neither fence checks facts. Both only control which continuations are eligible for the random draw. Return to the prism. Suppose our marker lands on spectrum. The token does not travel to a separate answer document. It attaches directly to the existing ribbon. Now, the context is longer. A prism splits white light into a spectrum. That changes the final position, so the model runs the causal transformer again and produces a fresh logit for every vocabulary token. The next distribution might favor of, then colors, then a period. Each selected token changes the question asked on the following cycle. The first cycle is worth watching slowly. Context, final vector, logits, distribution, selection, append. After that, generation becomes rhythm. Compute, select, append, repeat. Even if an interface streams several characters at once, the underlying decoder-only pattern remains autoregressive. The continuation is built from successive token choices. Implementations can reuse cached intermediate computations to make this faster, but the conceptual dependency remains. The next choice depends on the tokens already selected. This explains something subtle about fluency. A long answer can look planned because each local choice is conditioned on an increasingly rich prefix. Earlier choices constrain later ones. The model can maintain a topic, close a sentence, or follow a pattern without storing a secret completed paragraph. It also explains why an early odd choice can bend everything that follows. Once a token joins the ribbon, it becomes part of the context. Later, tokens must continue from that new branch, not from the answer we wish the model had chosen. And here is the crucial limitation. The tallest probability bar means most likely under this model and this context. It does not mean most factual, safest, or best. A fluent falsehood can be a very likely continuation. A true but unusual fact can receive less probability. Selection methods can trade consistency for variety. They cannot turn next token prediction into verification. So when an LLM writes a page, picture one evolving ribbon. The current tokens pass through a causal transformer. The final position becomes vocabulary logits. The logits become a distribution. A rule selects one token. That token joins the ribbon, and the loop begins again. One local choice at a time can produce a remarkably global-looking answer. But we have described inference, when the model must choose a continuation. During training, the text already tells us which token actually came next. The model can compare its distribution with that known target. So how does one wrong prediction change billions of weights? That is the next episode.